and then when you maybe shouldn't use it, and what else you should consider before just going in straight into it. So basically, passive DWDM is a dense wave division multiplexing. There's also coarse wave division multiplexing. DWDM lives in the 1550 nanometer band, and if you're going to have a true passive system, there shouldn't be any active components in order to make light get from one end to the other. So a couple of reasons for using DWDM in a passive state would be the cost. Passive DWDM is very cheap. You don't have to buy extensive shelf systems with, varying cards just to get that light out into your dark fiber. There's little complexity at all. It's pretty much just plug and play. You take your fiber from your gear and you hook that straight into your shelf, and then your line side fiber, whether it be dark fiber from a carrier or it be fiber across your campus, you just plug that into the usually DMUX or MUX port on the corresponding shelf. No provisioning. Support-wise, there's nothing. No additional support contracts. There's really, you don't even have to plug it in. So if you do have any problems, you're going to pretty much just keep troubleshooting the same gear that you're used to troubleshooting. And then density-wise, these systems are very modular. So you can easily get from an 8 to a 64 wave system, and all it consists of is just a 1U rack mount that can usually hold 16 shelves or 16 waves in a shelf. The only downside is if your gear doesn't support XFP optics and they only support SFP plus. Right now there are no widely available SFP plus DWDM optics, so you have to go the CWDM route. Here's actually a picture here of how you would configure this. Equipment-wise, you can see the shelf on the left is the line side fiber, and then each one of the individual fibers on the top is, say, transmit, and the bottom is receive for the given wavelength. If you buy a higher-end unit, because there will be some standard ones that don't give you monitor ports, higher-end units will provide you with a monitor port that will give you additional capabilities as far as potentially using an EDFA or the line side OIR. Here's a quick little sample topology. I wanted to point something out with this to you, is that since the shelves are pretty much unique to one another, if you have two pair of fiber, you could use the same color optics in one chassis multiple times. So that that way it allows you to have less sparing of optics, because the optics are a little pricey. So this way you could have two of one wavelength, two of another, and that way you don't have to waste money on having 4 different colors and 4 different spares. A little bit of information on the optics here. Just like the 10 gig LR XFPs, they have pretty much the same reach availability. So they say 10 kilometers, but in optimal conditions you can usually push them 25 kilometers easily without any kind of amplification. You can see the wavelengths. It is a higher wave of light than just a standard LR optic. Uses the same single mode fiber that you would use, you probably already have in your fiber plant. So it's really easy to make the transition. And then, the one way to tell these out, you can see in the image here, is the bottom optic is the XFP optic, and they usually have the white lever. So when shouldn't you use passive DWDM? Well, the first question is, do you have fiber that's readily available that you could push the slide across? If not, you may have to purchase dark fiber between sites, and that can be a little expensive. Again, you have to kind of weigh it now. If you do need to buy the fiber, is it worth buying the shelf or shelves that you need for the capacity? And then also the optics, depending on your vendor, they list at 10,000, but realistically, you can get them from most vendors between 3 and 6. So, that's another cost potentially. And then in other countries, like the European Union, I was talking with Remco, Metro dark fiber is so cheap there that in some instances it's not a worthwhile venue to use this dark fiber and passive DWDM. Plus, your vendor may not have optics that are supported. Only other considerations, if you need redundancy, this won't give it to you out of the box, so you have to duplicate your build-out. There may be distance limitations where you would be required to use EDFAs, and if you were trying to go with a pure passive system, then it wouldn't necessarily be truly passive. Port availability, if you are going to be creating a redundant configuration, you will need double the ports on your gear, and that may not be available. Also, if your fiber gets cut, you lose everything, whereas if you had an active solution that may have a protected path, it would automatically switch over. Another downside is, the vendors sometimes have a 12-plus week lead time just to receive the optics. So if it's a rush thing and you need to get this up, you have to plan for it. And then without any kind of active equipment, you won't get any OIR from this other than what the gear that terminates the fiber on each end provides you with. And just as far as the other reading go, Raz had a good presentation back at Nanon 48, just covering a lot of the physical layer stuff with the optics and fiber. So, anyone have any questions? Okay, thank you.
Next one up, Linda. Yes, please. Yes. And while we're doing the transition here, I am asked to remind you all to fill out the surveys. Survey. That is your way of influencing the program and the conference next time. Okay, Linda. You are...
Not this one.
Not this one. Not this one.
I have it. I sent this one.
Yes, I know.
You want me to use my laptop?
No. It's going to be here. Sorry, Sue, I can't find it. Yes. No. Sorry, Sue. Sorry about this, guys.
Oh, yeah, this is the one. Okay, good afternoon. My name is Linda Dunbar. Here I'm presenting this joint lightning talk together with Sue Harris down there. So this is talking about the network issues in the data center or cloud data center and some potential enhancement. This is actually quoted, this particular page, the partition or the breakdown of the cost in data center. We can see that in data center today, network itself is really only 15% of the total cost. Majority of the cost are on servers, power consumption. But network itself actually create a big barrier for the data center's agility and flexibility. As we heard from the talk from before lunch, we can see that in order to enable hosts to be moved anywhere in the data center, and they have to crack into servers, changing code so that enable the host, like the load balancer, to across different part of the data center. So this is in one of the research paper. They're saying that network innovation is actually the key to enable the data center scalability and agility. So network itself, we don't have to make it so rigid to confine the servers into certain locations. Okay, Why large layer 2 is the problem? And we see that in the talk before, that layer 2 traditionally is confined into a smaller domain because of within layer 2, there are lots of broadcast messages. The broadcast messages cause traffic, bandwidth utilization, and causing the switches to handle the traffic. So one of the biggest broadcast messages within layer 2 is ARP messages. So the message itself, basically servers and hosts frequently sending out those ARP requests. And many servers and hosts, their behavior are very unpredictable. So some are sending more and some are sending less. And especially under some uncertain environment, like software reboot or virtual machine starting up. Sometimes you want to start several virtual machines. Depending on the application, some of them sending a lot more than others. That's the primary reason that we want to keep the layer 2 confined. In this picture, you can see that traditionally in traditional layer 2, traditional data center network, that each layer 2 is confined into a few switches, few switch ports. But for many of the energy or resource aware algorithm, they try to minimize the number of servers being used. Because the virtual machine technology and server being virtualized, hosts can be created and deleted on demand very easily. And they can even be moved from one location to another location. So by moving the host, consolidating them into confined locations or any locations, you can shut down servers, you can even shut down switches. So that can better utilize the resource you have in data center. So when you want to move those hosts to different aggregation switch, different racks or different rows of in the data center, the traditional way of breaking a large network into smaller subnets no longer work anymore because the broadcast messages are sending through the core part of the network. And switches and links are exposed to broadcast messages from different subnets. So in this case, the ARP messages will be flowing into the core part of the network. Okay, here is another issue of the ARP problem in the network. When virtual machine moves, migrate, some of the migrations out of service migration. So during the transition, there will be other hosts sending the ARP requests and without any response coming back. And then they were repeatedly sending those requests, causing more messages in the network. And when the VM moved to the new location, there will be gratuitous ARP being sending out. So here just talking about some possible ways to refine the broadcast messages. So that broadcast message in traditional network is confined to layer 2, confined to one subnet. And here we're talking about you don't necessarily have to do that. You can confine to smaller location, smaller domain when the layer 2 span across multiple racks or multiple rows. Or you can use a directory-based approach, which can be centralized or distributed method to do this ARP, which is like layer 2, layer 3 kind of glue protocol. Okay. Here just talking about why this is better. But our main intent actually is to create a new working group in IETF we call ARMD, which is address resolution for a massive number of hosts within the data center. So initially, we try to document the scalability of ARP and ND. ND is for IPv6, with increasing number of hosts in the data center, and identify limitation of those protocols, and provide design recommendation and how to minimize the issue. And secondly, maybe phase 2 is potentially develop some solutions to better support data centers with large number of hosts and with the desire of letting hosts to be placed anywhere in the network. So that's the end. Any questions? Actually, we are looking for feedbacks.
Hi. Hi. Dave Meyer. have you considered, I mean, I followed the RMD mailing list, so I got a pretty good idea of what's the discussion's about. But if you look in the really large scaling things in really big data centers, you can't really broadcast anything. So the reality is, you know, anything that, and this includes things like DHCP. So have you considered the possibility that ARP as we know it today is not the answer to this?
Well, I agree that ARP is not the only problem when you allow hosts to be placed anywhere in the network. It's definitely not the only problem. But in IETF, every time they create a working group, they want a very small, focused working group. That's why we drill down to ARP. And it's one of the issues. It's not the only problem. DHCP is another issue, too.
I would say that, well, the ARP, you know, ARP scaling is one issue. VM mobility is, you know, something different. So can be solved by ARP in some ways, but.
Agree. Okay.
So Dave, you've suggested that Suhair's, Dave, you've suggested that ARP can solve it in some ways, and I think what we're looking to see is what pieces ARP can solve in the general situation and in mobility. It's clear that it can solve some mobility problems, it cannot. One of the first things we're doing is looking at the actual statistics from actual networks, and we'd love to talk to anyone. As you just saw before lunch, we had Yahoos facing the general problem. So I think our first thing is information gathering that we can publish and discuss. We've had a lot of private discussions, but I think we're trying to first get public data that we can debate and then go from there.
Okay. Just one point I want to emphasize is for problem in data center, there are many different approaches to solve it, right? As we saw in the talk by Yahoo before lunch, their approach is to change DHCP and change the server, so allow the virtual IP to be on different locations. That's the ultimate goal, right? Allow those hosts to be anywhere in the network. And our approach is just slightly starting from the network, the layer 2, layer 3 glue part, and to make them scale to allow that happen without all those broadcast messages floating in the links and switches. Okay.
Thank you. Next we have Ken.
How does this thing work? How do you make it big? There's usually a thingy down here, isn't there? Yeah, there it is.
Slideshow.
Oh, yes. Hi, I'm Ken Florance from Netflix, and I'm going to talk to you about a blog post we did. We've gotten a bunch of questions on it, so I thought it might be a good idea to stand up here and take some more, maybe. So basically, a couple of days ago, we posted on our tech blog some information about what we see in terms of Netflix performance on various networks. And what I'm going to do is go through kind of how we do it, why we do it, and so a little more detail on how it all works. So what we do is all of our streaming clients are either written by us or based on an SDK that we put out. And in that SDK, there's lots of specifications about what we want to log, including a lot of performance information. And as we get those logs back, we capture the IP address from the clients that we're connected with and assign an AS number to those IP addresses. And then using that, we group by network and assign the performance characteristics to the various networks. So basically, the clients are talking to a bunch of Netflix servers in the AWS cloud. Those Netflix servers then pass along the logs to a Hadoop cluster that does a MapReduce on them. That data, processed data, is then piped back to our data warehouse and our Netflix data centers, and then we have some reporting servers that can kind of slice and dice it for us. So why do we do this? We're kind of in this interesting position of getting a tremendous amount of long duration, high definition views. So really seeing what can be supported in terms of sustained throughput on these various networks. Obviously, we get a lot of questions, both anecdotally and through many other means, friends, about how performance works. What does it mean when their client pauses, et cetera. We also get a lot of questions about, do we feel like any of the networks are manipulating our traffic in any way? And so we felt like this would be a good way to just kind of get some data out there in public, and we don't see any evidence of that to date. And it also obviously helps us understand how the performance is changing over time and what we can expect as time goes on. So there's a lot of stuff we'd like to do better here. One way is to make a slide with that many lines readable is a little bit challenging. So if anybody's like particularly good Excel foo that they want to share on how to do that, I'm open for suggestion. Also, we've gotten a lot of comments about something that we knew was going to be an issue when we put out the chart but didn't have a good answer, which is AT&T and Verizon have obviously a lot of DSL offerings and also a lot of fiber offerings. And since we're doing this by AS number, we don't have a good way right now of splitting that out. So if anybody from either AT&T or Verizon or anybody else has any good ideas on how to help us do that, I guess we could figure out what IP blocks are being used for what and try and post-process the data. Like to avoid that if possible. But anyway, open for input on that. Didn't get the memo that Embark and CenturyTel were CenturyLink when I put out the slide, so we've got to fix that. And there's lots of other interesting metrics we'd like to look at over time. We track internally not only time-weighted bit rate, but rebuffers, how many rebuffers per session hour we get from clients. We're working on some possible composite metrics, but we've got a lot of interesting data to carve through and always looking at better ways to kind of understand client performance and how we can improve it. Only put 4 Canadian ISPs on the original Canadian chart because they were the 4 Canadians that fell in the list of top N ASs that we're looking at. We want to dig deeper into that, and then obviously there's a lot more that we could do to improve. So here's the almost readable chart. Any questions?
When you send out an email that asks, how was your streaming experience, is that triggered by metrics you see, or is that purely random?
It's random.
Okay.
It's basically we're just always looking for people's input. We found that was a really good way to identify streams that had encoding problems and stuff like that. So it's kind of a QA thing for us. Anybody else? Okay, we're done.
Thank you very much.
Thanks.
Thank you. And next up is, there's a question there?
There's no mic at that end anymore. So I'm Dylan Curley from Google. I have a question about, I know that a number of geo-IP sources have, as well as ISP information, they also break out blocks by tier of service. And have you used that? If you have or haven't, what have you experienced? And
we do, yes, I think we do get that from our geolocation. I don't have that wired into Parson yet, but I haven't used it, so I couldn't speak to the reliability of it. What I recall is it's, at least the last time I looked at it, it's not that interesting. It was kind of like, showed a couple of low tiers and then everything under over 2 megs or something was high speed or something. But I don't know, I'll have to go back and look at that.
Okay, thank you.
Yep.